See, in the previous lecture, we have discussed how molar conductance and equivalent conductance defined and specific conductance is defined, and variation of molar conductance with dilution and equivalent conductance with dilution and specific conductance with dilution. Specific conductance, it is decreases because it depends on the number of ions present in unit volume, and molar and equivalent conductance increases with dilution. It is clear now. uh, we are now I am adding this point here: strong and weak electrolytes, and how this variation in molar and equivalent conductance is taking place with dilution for strong and weak electrolyte. Can we decide the nature of strong and weak electrolyte on the basis of this molar conductance? So I am trying to answer all these questions. So see, first you have to develop the idea of what is the meaning of dilution. So suppose that if you have an electrolytic solution, right? Suppose that we have AB, an electrolyte, right? And we have taken 1 mole of this electrolyte, 1 mole, and volume, let it be, the volume is here V liters, right? So what is the concentration of this? So the concentration of this is equal to, C is equal to 1 mole divided by volume in liters. Volume in liters. So what we have to do here, fix the quantity of electrolyte 1 mole and make this volume free. Means this is variable. So as per this V is changing, the C also changing, because C depends on these two factors. This I have taken, I have made this 1 mole because we want to consider this electrolyte, because in if you see in equivalent and molar conductance, in both the cases we have taken what, 1 mole of the electrolyte, 1 mole of the electrolyte. So this term, when you have fixed the quantity of electrolyte 1 mole and this volume is free now, so this term is now you can replace with the dilution. So this is equal to, you can write 1 mole by dilution. Dilution, right? So basically take the fixed quantity 1 mole of any electrolyte in some quantity of solution. Now you can add water to increase the volume of solution, because this is variable. So now this volume becomes this volume is now known as a dilution. So if we take this electrolyte, so and here on x-axis we can take dilution, and here molar conductance, right? So what will happen when we increase this dilution? So we get graph like this. Like this, right? So if you interpret this graph, what you can say that, okay, this molar conductance increases with dilution, right? Molar conductance means the interpretation, I am writing the interpretation of this graph, that the molar conductance increases with dilution, right? So the question arises immediately, why this is I mean increases. So you can make a logic that with dilution the degree of dissociation increases. So this is due to increase in degree of dissociation. Degree of dissociation means the molecules dissociated, and if the number of molecules dissociated increases, so the number of ions increases, so molar conductance increases. Got it? Clear? Okay. One more question arises here. After a certain time, we'll see the molar conductance becomes constant. So after certain point, certain point of dilution, the molar lambda m constant becomes constant. So again, the question arises, why this is constant? So what logic we can put here? We can say that whatsoever the number of molecules we have in 1 mole of the electrolyte, means Avogadro's number of molecules, all the molecules gets dissociated. Once the all molecules gets dissociated, number of ions now fixed, and if number of ions are fixed, molar conductance will constant. This is the simple logic. So why? So we can make a logic here due to the fact that all the molecules all the molecules gets dissociated. So once all the molecules gets dissociated, number of ions constant, all the molecules dissociated, so number of ions are constant, and once the number of ions are constant, molar conductance becomes constant, right? Now it is clear. Okay, when we see this molar conductance for another type of electrolyte, we will get this, and keep on dilution, increase on dilution, increase the dilution, increase the dilution, slowly this will increase, this will increase, this will increase. So what argument we can compare between these two? Suppose that this is y electrolyte and this is x electrolyte. So what we can infer, what we can find the conclusion regarding these x and y. So we can say that okay, x may be a strong electrolyte, that's why it easily dissociated and easily attains the maximum value of molar conductance, and Y should be a weak electrolyte, because in Y this is increasing, increasing, increasing. When this will attain the highest value, we cannot easily predict. So definitely this could be a strong electrolyte, and this is a weak electrolyte. So on the basis of this plot, you can say this is strong and this is weak electrolyte. And you know, the maximum value of this molar conductance, whatsoever we are getting here in case of strong electrolyte, that is called lambda m infinite. Lambda m infinite. And the volume corresponding to this is called infinite dilution for strong electrolytes. So can we make an argument that okay, means this is one of the definition of strong electrolyte and weak electrolyte, we can make that strong electrolytes easily attains the state of infinite dilution, means complete dissociation. Infinite dilution, right? Due to the fact that all the molecules get dissociated, and this state of dilution in this situation is called infinite dilution. Infinite dilution. So whenever the word used infinite dilution, you should read that, or you can perceive that like this, means all the molecules gets dissociated. So we can make an argument that here strong electrolytes achieve easily easily the state of infinite dilution, right? They easily achieve the state of infinite dilution, and weak electrolytes probably not. Hmm? Probably they cannot achieve the state of infinite dilution, right? So this is the, observation regarding the molar conductance and equivalent conductance for what strong electrolyte and weak electrolyte. Now see, increased dilution due to the degree of dissociation, due to the increase in degree of dissociation. See again here some discussion. So and means few molecules are dissociated and some molecules are undissociated in this situation. But at this point, when this has the maximum value, then the total molecules dissociated. So at any moment of time, if you divide lambda molar at particular concentration by lambda molar at infinite dilution, this corresponds the total molecules dissociated, and this corresponds the molecule dissociated at in particular condition of dilution. So this is called alpha, degree of dissociation. Degree of dissociation, because you know this lambda mc, this is the molar conductance, molar conductance uh, associated with associated with molecules molecules dissociated at particular concentration, at particular concentration or dilution, right? And lambda m infinite is the molar conductance, molar conductance associated with total dissociated molecules. Total dissociated molecules, right? So you can find out the degree of dissociation for any given electrolyte, right? So see, in this molar conductance, Kohlrausch find a relation for any strong electrolyte. Similar relation, what I have stated here, but different terminology he has taken. So Kohlrausch law of independent independent migration of ions, right? So this is Kohlrausch law of independent migration of ions. What Kohlrausch find, see what Kohlrausch found for any strong electrolyte, for any strong electrolyte, I am taking here AB because if you take different electrolyte like A2B, A2, AB23, then there is a little change in the formula, and you will see after, but I am considering this AB. So this will true for every time. So lambda m at any particular concentration C is equal to lambda m infinite minus B root of C. So what I have defined you here, V in a general formula, C is equal to 1 by V. So he has taken root of C, and now you can put here in place of C, root of C, 1 by V, right? That is equal, but this is what Kohlrausch explained. So this is the molar conductance at particular concentration C, and this is the infinite dilution. So what he found, when you make a plot between this and this, where B is a constant determined experimentally, B is a constant determined experimentally, and it is positive basically, not negative. So this is always positive. Okay, so if we make a plot, and we can determine between by plotting this and this value. So if we make a plot, lambda m and root of c. So for any strong electrolyte, we are getting this type of this type of plot. And if we extrapolate this graph, so this will cut this axis at this point. So this is called what? Lambda m infinite, right? And this point is the you can say infinite dilution, because root of c is increasing here this side, so the here this is what, very low concentration. So for strong electrolyte, we will get this type of graph. But for weak electrolyte, this type of variation. So this will not cut this axis at any point. So this is for weak electrolyte, right? So I think we cannot make this determine experimentally this lambda m infinite for weak electrolytes. But what this heading of this, see, the words used here, they are very very important. See, Colora's law. Colora's is the name. Law is normal word. See, independent. This word. This key word of this law definition. That what is the meaning of this independent? What Colora's observed, that okay, for strong electrolyte, we are able to find the complete dissociation state easily. Means we can determine lambda m infinite very easily. Yes, it is okay. And he stated that at infinite dilution, since the electrolyte is fully dissociated, so every ion is independent. See, this is the word used here. Independent migration means now that ion is free from the legacy of its electrolyte. Means that ion is derived from which electrolyte, that is immaterial. Now, when? At infinite dilution. So at infinite dilution, every ion is independent of the source, independent of the electrolyte from which it is derived. So this is very important conclusion. So suppose that you have acetic acid. Acetic acid constitutes acetate ion and H plus. And if you have molar conductance value at infinite dilution for H plus, that H plus not necessarily derived from acetic acid. That H plus may be derived from any strong electrolyte like HCl, like H2SO4. But if you have the value of lambda m infinite for H plus, and if you have the value of lambda infinite for acetate ion, not necessarily derived from acetic acid, it may be derived from some other strong electrolyte like sodium acetate. So if at any point of time you add the values of lambda m infinite for H plus and lambda m infinite for acetate ion, so this will give the lambda m infinite for acetic acid. What is the problem? That's why this law is very popular. So you do the experiment for strong electrolyte, note the values for every ion, make the list, and now make the permutation and combination of ions to make the weak electrolyte. And by doing that, you can find out the molar conductance of weak electrolyte at infinite dilution. So there is no need to do the experiment for weak electrolytes to determine lambda and infinite. You just do the mathematical manipulation on paper from the data of strong electrolyte. So this is the key word of this definition. Independent migration means every ion contributes in the molar conductance independently at infinite dilution in strong electrolyte. And by using that data, we can calculate the lambda and infinite for weak electrolyte. And any value in between value we can determine experimentally for that. So we can very easily determine alpha for weak electrolytes. And this is the method used to determine alpha and equilibrium constant for weak electrolytes. Understood? Clear. Okay. So what is this Kohlrausch law? Kohlrausch law is at infinite dilution. So we can write here at infinite dilution, infinite dilution, the molar conductance, the molar conductance of an electrolyte is equal to the sum of molar conductance of cation and anion. I am taking AB type electrolyte. That is every ion contributes independently in the molar conductance. Molar conductance. Right. So you can write here that this AB is an electrolyte. At infinite dilution, this is fully dissociated, means this is nil. And suppose that we have taken 1 mole of this. So we have 1 mole and 1. So at any moment of time, lambda m infinite of AB is equal to lambda infinite of A plus lambda infinite of B minus. Right? So you can write like this. Similarly, suppose that your electrolyte is AXBY type. So when this will dissociate. Now see, this is the chemistry. If you do not know how to dissociate this electrolyte, your answer, difficulty for you. This is difficult for you. So this will dissociate like this: XAY plus YB X minus. Now the molar conductance of AXBY at infinite dilution, this is equal to X times of the molar conductance of AY plus Y times of molar conductance of BX minus. And if you want to write equivalent conductance, because equivalent conductance is more important, more simple, like normality and molarity, right? If you write the equivalent conductance, but this IUPAC have scrapped this equivalent conductance terminology. They, I will suggest that you have to make the formula in terms of molar conductance. But it is easy to do the calculation, because this equivalent conductance, this is equal to lambda infinite of AY plus EQ and lambda infinite EQ of BX minus. This is equation 3. See, what is the difference between these two? The difference is the coefficient. This balancing is not required when we are using this concept of equivalence and mil equivalence. The same case here also. So I have written here the equation for both in terms of both equivalent and molar. This is in terms of molar conductance, and this is in terms of equivalent. Whatever you find easy, you can use that. Okay. So this is the, I mean, what Kohler's law of independent migration of ions. Now see what is the application of this law. Application is to calculate the molar conductance at infinite dilution and equivalent conductance at infinite dilution for weak electrolytes. Which is not possible by what this experimentally it is not possible, but theoretically, mathematically we can do that by applying this Kohler's law. Now see, suppose that you have HCl, and molar conductance at infinite dilution for HCl is equal to X ohm inverse centimeter square per mole, right? And lambda infinite for NaCl, this is equal to Y ohm inverse centimeter square per mole. And lambda infinite of CH3COO this is equal to Z ohm inverse centimeter square per mole. Suppose that this is given. So this you can write, this is equal to lambda infinite of H plus lambda infinite of Cl minus by Kohler's law. By Kohler's law, you can write this. Now all are strong electrolyte, and here you can write lambda of Na plus lambda of Cl minus, and here you can write lambda of CH3COO minus plus lambda of Na plus, right? So this is equation 1. This is equation 1, this is equation 2, and this is equation 3. Now see, if you manipulate this equation in such a way that you should add 1 and 3, equation 1 plus 3 and minus 2. So what you get? Lambda infinite H plus lambda infinite Cl minus plus lambda plus lambda infinite Na plus minus lambda infinite Na plus minus lambda infinite Cl minus. This is equal to x plus z minus y. Now see, this Na plus cancel, this Cl minus cancel. So what is left? The molar conductance of H plus at infinite dilution plus molar conductance of CH3COO minus. This is equal to, you can write lambda infinite for CH3COOH, and this is equal to x plus z minus y, right? Ohm inverse centimeter square per mole. So this is the answer. Right? So in this way you can calculate the lambda m infinite for weak electrolytes, right? Okay, now see this question. This question is, very simple question. Calculate the molar conductance and equivalent conductance of PaCl2 in water, and in at infinite dilution this is given. So just simply apply Kohl-Ross law. See, a general expression I have given you. See, this is the general expression, right? So, but this expression you cannot use. Why? Why this expression you cannot use directly? Because you know the value here they have given molar conductance. Individual values they have given for molar conductance. So you cannot use this equation directly. This equation, but this equation you can use directly. So first you calculate this molar conductance, and after that by using n factor you can convert this equivalent conductance. So this is very simple question. So see, so first you have to write the expression for as per the Kohl-Ross law, molar conductance for barium chloride. This is equal to lambda infinite Ba2 plus twice of the molar conductance of Cl minus at infinite dilution, and it is the value is given. The value is given. So this is equal to 12.72 into 10 to the power minus 3 plus 2 into 7.63 into 10 power minus 3. So this is equal to, see, this is 2 into 7.63 is equal to 15.626 plus 12.72. So 27.98. So this is equal to 27.98 into 10 power minus 3 Siemens meter square per mole. Right? So this is the answer. And equivalent conductance and molar conductance, how they are related? See, lambda infinite equivalent conductance is equal to, see here, one relation in the last lecture we have developed. See, molar is equal to equivalent into n factor. So equivalent is equal to molar by n factor. So here you can molar of BaCl2 by n factor of BaCl2. So molar we have calculated, already calculated this 27.98 into 10 power minus 3 divided by 2. See, BaCl2, it is a salt, so Ba2 plus 2Cl minus, so N factor is equal to 2 because total positive charge or total negative charge. So this is equal to 2 13.99 into 10 power minus 3 Siemens meter square per equivalent, right? So this is the second answer. Okay, so in this way you can very easily calculate such type of questions. Okay, good. See, another application of Kohler's law, determination of solubility of sparingly soluble salt. So suppose that we have a sparingly soluble salt AgCl. So all of you are knowing that this AgCl will form an equilibrium with its dissociated ions Ag plus solid plus Ag plus aqueous plus Cl minus aqueous, right? Like this. So at given situation, and you know this solubility product that depends on temperature only. So at constant temperature, the maximum dissociation is given by the KSP. So whatever molar conductance we are getting at this point at in this saturated solution, so that is the solubility of this. So whatever the molar conductance at this situation, whatever we are getting, that is equal to molar conductance is equal to kappa into 1000 divided by, we can put here in place of molarity, we can put solubility, right? This is because you know whatever here it is given, and sometimes the examiner may give you the infinite dilution, because this AgCl, whatever the maximum value it can be dissolved at given temperature, that is dissolved here. So this is the maximum conductance. So sometimes you may get here infinite, right? And this is in place of molarity, you can take solubility, and now after getting solubility, you can use the ion solubility product by using this general expression KSP is equal to x to the power x, y to the power y, s to the power x plus y. So uh, by determining solubility S from here, this equation put here, and if you and the nature of salt is AXBY. So for any given AXBY type of salt, by using these two equations, even you can determine solubility product as well, right? So whatever conductance is given in the given saturated solution of any sparingly soluble salt, that will give you the directly solubility, right? So by using this equation, you can determine the solubility directly and solubility product as well. Okay. So in this way, you can determine solubility product for sparingly soluble salt. Now, see, I have shown here some data for the equivalent conductance and ionic mobility. Both data is there. If equivalent conductance for any given ion at infinite dilution is more, then ionic mobility is also more. Very remarkable point. See, if you see here, this for H plus, uh, this conductance, equivalent conductance or ionic mobility. And for OH minus, for this OH minus, this ionic mobility is maximum. See, for H plus maximum, after that OH minus, and after that you will get for different ions. So if you carefully observe this table, you will find that okay, molar conductance or equivalent conductance or ionic mobility for H plus is highest. How this can be explained? So and suppose that if it is asked, okay, tell me electricity will conduct in water maximum or in ice. Now tell me if it is asked that the electricity will conduct faster in ice or in faster in water. So the answer is ice, because this highest value of equivalent conductance, this is attributed to the hydrogen bonding. So if your molecule have more hydrogen bonding, then this conductance is more. So in ice, this H plus, the movement of electricity through this H plus ions, in one step, this will move 9 water molecules away. So I am going to show you how this H plus shows the highest molar conductance or equivalent conductance or ionic mobility through hydrogen bonding, right? So suppose that if we have water molecule, suppose that if we have water molecule like this, O H H, and this H plus is bonded here, right? This is the H plus. Okay. Now this hydrogen is bonded with this oxygen, and here hydrogen bond. Hydrogen bond. I have taken here only 3 molecules of water, and H plus is here attached. All of you are knowing that this H plus is moving, exists as a H3O. Now see how this H plus is migrating. A wonderful, mechanism given by Hittroff, right? See, now this hydrogen will attach with this hydrogen. This hydrogen will attach with this, uh, uh, and here hydrogen bonding will come. So this hydrogen now becomes the part of this water molecule, part of this molecule, and here there is a hydrogen bonding. Now this hydrogen becomes the part of this molecule, and positive charge will come here. Now see the hydrogen bond now between this. So see the change of hydrogen bond. Only two hydrogen bond, this hydrogen bond and this hydrogen bond. Change of this hydrogen bond makes the shift of H plus from here to here. Positive charge will move. See, a wonderful mechanism to explain this the movement of H plus. Now you cannot say that this H plus will cleave from here and then move like this through the system. Not like that. This hydrogen bonding is playing an important role here, that between this H and O, this hydrogen bond is, this bond is cleaved here. Now this hydrogen make a covalent bond with this and hydrogen bond with this. See the change. So what is happening here? Some of the covalent bond converted into hydrogen bond and hydrogen bond into covalent bond, and due to this, virtually H plus is moving from this end to that end, and this is the reason why in ice electricity will conduct more than in liquid water. Now it is clear. Okay. So this is the method. Why this is the explanation why H plus has the highest equivalent conductance. Why H plus has the highest equivalent or highest ionic mobility. You can say mobility. And similar explanation for OH minus as well. Similar explanation for OH minus. See how? See, this is OH minus and HOH, right? And HOH. Now see, there is a hydrogen bonding between this and hydrogen bonding between this. Now change in hydrogen bond. See, so this H O H O H H O H, right? See, so this is the method how this H minus and OH minus have highest ionic mobility. So a hydrogen bond play a very important role here in the migration of H plus and OH negative ions in aqueous medium, right? So this is the reason why H plus and OH minus have very high molar conductance or equivalent conductance or ionic mobility.